So we're going to start the final week of the semester by talking about responses to the cold. So Tuesday will be about the cold, Thursday will be about altitude. So we're going to start off with the acute responses just like we did with the heat. So here are the objectives and outcomes, and it's essentially the same that we had for the heat, and it will be the same for the altitude, only we're talking about the cold this time. So if you recall, last time we talked about how when we're in the heat, skin blood flow is increased so we can dissipate heat. So here we've got this cool little animation that I stole from one of my advisors for my master's work. And so we've got red blood cells traveling through the bloodstream, and as they do this, and as the blood, not necessarily the blood cell, it dissipates heat. Okay, but in the cold, these vessels vasoconstrict, and so as a result, the blood preferentially goes to the vessels that are underneath the fat. And yeah, they release heat, but the fat insulates and keeps that heat in there. Okay, and so that helps keep the core warm, protects our vital organs. So, just to kind of recap, when our core temperature decreases, the skin blood vessels vasoconstrict, which decreases skin blood flow. Now, this happens everywhere, not just in the skin, but because it happens in the skin, we're able to hold on to that heat. The one place where we really don't have vasoconstriction is in our scalp, because those vessels don't really constrict or dilate; they're just there. So this is why one of the reasons why we wear hats or beanies in the cold, because we're always losing heat from our extremities and specifically from our head. And so, regardless of what's going on in the head or not, blood flow will be redistributed. Okay, and so what ends up happening, as I said just a moment ago, is that we're going to pack the core or our central blood volume, that's going to increase. And then this actually causes some changes. And so if you have a lot of blood in your core, that's going to increase venous return. When you increase venous return, that's going to increase stroke volume. Those baroreceptors are going to be activated because we have high blood pressure. And so we don't like having high blood pressure. We want to have normal blood pressure, and so we're going to counteract this. And the quick answer of how we counteract this in the cold is that we actually increase urine volume, and this is referred to as cold-induced diuresis. Okay, so due to all that extra fluid that's in the core, it's going to increase the pressure. We want to alleviate that pressure. And remember how we talk about water balloons all the time in my classes. There's two ways that we can alleviate pressure from water balloon. One, we could stop squeezing it, or the other way is to take fluid out of the water balloon. And so that's what we're doing here, is we're peeing it out. So blood pressure is decreased. So if we go to the Fick equation, VO2 max equals cardiac output times the AVO2 difference. So if we look at that, VO2 max equals heart rate max times stroke volume max times the difference in content between the arteries and the veins. So if we're going to have any impact on VO2 max, core temperature must be below normal. Now, if you think about it, when we go exercise out in the cold, usually we bundle up, right? So I've got layers, I've got leggings, and I've got a thick insulated shirt. And then if it's really cold, I've even got a pair of fleece pants as well as a top. And then I wear gloves and a hat and that sort of thing and to try and keep my core temperature normal. And so if I do that and I'm able to maintain core temperature, I'm not going to have any impact on my VO2 max. It is possible, or what can happen in the cold if our core temperature decreases, is that max heart rate might decrease. Okay, and we don't compensate for this with a change in stroke volume, so as a result, maximal cardiac output is lower than what it would be in a normal situation. Additionally, we have a left shift of the oxyhemoglobin curve because of the cold temperature, so this causes oxygen to be held onto or to bind with hemoglobin more tightly, so we have increased affinity, which means it's harder to unload. And as a result, we actually decrease the amount of oxygen that's being delivered to the tissues. So again, if we go back to Fick, and I'm not going to go back just because of all the animations, but Fick is cardiac output times the difference in oxygen between arteries and veins. And so we've shown that heart rate decreases, stroke volume might remain the same, but then what's taken up by the tissues is reduced. So we've got two of those three variables that are being affected by the cold. And it's also possible blood flow is going to be decreased to the skeletal muscle because we're trying to keep ourselves warm, trying to maintain core temperature, which will decrease oxygen delivery. So there's several different ways why VO2 max might be impacted. Now, kind of tie that into endurance performance. Again, if our core temperature doesn't decrease, all bets are off. But once the muscle starts to cool, fatigue, the way that fatigue develops changes. And initially, that's not a bad thing. So if we have just slight decreases in muscle temperature, fatigue occurs more slowly, which is great. However, if you get really cold, so your muscle temperature falls below 27 degrees Celsius, which is high 80s, then your endurance decreases. And this is likely due, although not completely understood, but it's likely due to the fact that action potential will travel more slowly. And it's possible that because of this and just because of the cold itself, we're not recruiting as many muscle fibers. Okay. We're going to talk about this, I think, a little later, but like, for example, one of the things that's going to happen or can happen is that when your muscle cells are cold, the sarcoplasm or the cytoplasm or the fluid inside your cells kind of turns to jello, and it's just harder for things to move. It's more difficult. And so there's an important paper that was done 25 years ago, which is kind of surprising. A study done by a couple people out in England, Galloway and Mon, and what they were trying to find out is what is the best temperature for aerobic performance or endurance performance. And so they had people do basically time to exhaustion time trials in 4 different temperatures, so 4, 11, 21, and 31 degrees Celsius. And so this is about 41, about 51, 69, and like 87 degrees. And what you can see here is that time to exhaustion in that kind of time trial, that it appears that around 11 degrees Celsius or about 51, 52 degrees Fahrenheit had optimal performance. But as we get away from that temperature, whether cooler or whether warmer, time to exhaustion decreased, which means they weren't able to complete as much work. Similarly, this is that same study. What they found is that when we're in the cold, there's a higher VO2, so higher oxygen content or oxygen uptake at a given workload. And this was due to the fact that they found that skin thermoreceptors actually cause increase in tension or muscle metabolism. Okay, and this is likely due to something similar to shivering, where they're trying to generate or release heat to keep us warm. And so for a given activity, VO2 is higher in the cold, as we can see here from this top line, than it is in cooler temperatures. Okay. So when we take into account exercising in the cold, we have to account for other factors. It's not just the fact that it's cold. So as I said earlier, if I put on additional clothing, well, that's going to cause me to have a greater weight. In order to do something, it's going to cost more energy. And then when we sweat, we actually increase the weight of those clothes. So that'll add to it. And then you get what's called the hobbling effect. And so as I told you a little while ago, I put on a bunch of layers. That's going to change the biomechanics of my running. Okay. And admittedly, I would imagine that the gear that I have is designed for running, but it's still not the same running in tights and like these fleecy sweat things as it is if I just have shorts and a t-shirt on. And so as a result, I can't run as smoothly. My economy will decrease, which means my VO2 for a given workload will increase. And then you have to account for the fact that there's friction as this clothing slides across each other in order for it to move so that you can move. Now, if you're shivering while you're exercising, that's going to affect your VO2 as well. And so we've got this figure here. So we've got intensity on the x-axis, we've got VO2, relative VO2 on the y-axis, we've got thermoneutral in the red, and then we've got cold in the blue. And as you can see, for a given for a given intensity, VO2 is higher in the cold. And this is because if we're shivering, that adds to the increased oxygen demand needed to complete the activity. So not only are you running, but you're shivering, and that's never very fun. And so what happens, though, is that you hit VO2 max at a lower intensity and a lower value when exercising while shivering. Now, if you want to just look at muscle function specifically and the cold, as we mentioned, or as I alluded to a little while ago, things are different in the cold, right? So we've talked about how the temperature is a measure of like velocity of molecules. And so in the cold, molecules move more slowly. And so as a result, your neurons don't move or act as quickly. And so it just changes the way that we're able to recruit our muscles. Because of the cold, because of that viscosity, your muscles aren't able to shorten as easily. And so ultimately the power output from your muscles decrease. But like we said with VO2, if your muscle temperature isn't affected, even if it's cold, as long as the muscle is still warm, then your power production won't be affected either. So a little kind of flow chart to see it. So to see this is that when you get tired, you decrease your intensity, which means you have less heat production, which lowers your core temperature, which leads to even a greater fatigue. And so this is actually a positive feedback loop. And so getting cold or exercising in the cold and then getting tired, you can kind of spiral a little bit. When it comes to resistance exercise, hypothermia, and we just mean low core temperature, low muscle temperature, decreases muscular endurance, power, and strength due to things that we've already talked about. So your nerves don't fire as quickly, which means you're not going to be able to recruit as many muscles. It's going to take longer to reach that maximal force. Cross-bridge cycling is going to be decreased because of the viscosity or the thickness, the jello of your cytoplasm. Chemical reactions slow down. All of these, especially these last four things, kind of all go together to make it so it's difficult to reach maximal force. So to give you an idea of what the extent of it is, for every degree Celsius that your muscles, remember this is muscles, are cold, you're going to lose 4 to 5% in performance. Okay? And again, it's due to cross-bridge cycling. We come back, I know it's a joke in this class, a running joke in this class, but when it comes to these power output events or these high power events, it's all about cross-bridge cycling. We want more cross bridges and we want them to attach, reattach, attach, pull, detach, reattach, pull, go through that whole process. And if anything happens to slow that down or to reduce the number of cross bridges, we're not going to be able to produce as much force. Okay. And so again, we're hitting this hard that cold turns your muscle cells into jello kind of. And so just the act of cross bridge cycling is going to be, have a lot more difficulty occurring, as will the chemical reactions the enzymes use to allow for cross-bridge cycling. And so that is what we're going to end with on the acute responses to the cold.